Thanks so much for the invitation to speak. And it's really a great year at the Institute here. And there's so many visitors in probability and related fields. And so it's nice to come and join all of this. Okay, so I'll be talking about a process called the random stirring process, or sometimes the interchange process, depending on exactly what sort of area you're from. And you can think of it as a model of a sort of random permutation. So where it's a permutation, I guess, over the vertices of some graph G. And it's in continuous time, and at each edge of the graph has a rate 1 Poisson clock. And when the Poisson clock rings, you do a transposition on that edge and multiply that by that permutation. So that's how sigma of t, your random permutation, evolves in time. And we'll be interested in what the cycle structure of this random permutation looks like. But basically, I don't really want to think of this as a random permutation. We can also think of it has another representation as what I'll call a cyclic random walk. And so if I draw G, the graph on the x-axis, here it would just be like Z, and time on the y-axis. And I'll say that we're looking at time beta, which is a funny letter to use for time, but I'll sort of say why that's appropriate a bit later on. Whenever a clock rings on some edge, I'll put a horizontal line here to indicate that there was a transposition. So we'll get this sort of Poisson process of random transpositions. And now suppose I want to know, where does the origin go after time beta? Well, I would follow this up in time, and then we get a transposition. It gets moved to its neighbor, and then it has another transposition, gets moved to that neighbor, and in this case ends at position 2. So in this random permutation, 0 gets mapped to 2. Then we could say where 2 gets mapped to, or we go up, hits a transposition, goes to the left, hits this other transposition, goes to the left, and ends up at 0. So in this case, 0, 2 is one of the cycles of permutation, so cycle size 2. So in this way, you can sort of work out what the cycle structure of your random permutation at time beta by sort of following these walks on this graph at the horizontal lines. And so one obvious sort of consequence of this is that you can only move within the sort of connected component of edges that you have. So if your beta was small enough that you were, I guess, probability of having a transposition was less than PC, then you would definitely be in a finite component. So in one dimension, of course, you'll always have finite components or finite cycles orchestra. So I want to think of this cyclic walk as not on time between 0 to beta, but continuing for all time. So if I start off at time 0 and get to beta here, then I'll just sort of continue on, and as though we'd sort of repeated these transpositions, sort of mod beta into the future, and then at time 2 beta we get back to 0, and then the cycle closes. And so I'll call this process the cyclic walk, and we want to understand how that behaves, and in particular we'd like to show that it's transient. mean, I'll tell you what sort of things we want to prove. I can also think of this as being sort of driven by some underlying random walk, where, so from time 0 up to time beta, it's exactly a continuous time random walk. But after time beta, let's say when we're here, which corresponds to here, we already know, oh, okay, actually not there, when we're, I guess, yeah, okay, when we're here, which corresponds to down here, we already know that there were sort of no edges across here and then one edge there. So the walk is kind of interacting with its past. It's sort of and it's not sort of just seeing new independent jumps as you move on. So the coupling I want to sort of do is you say, okay, xt is a continuous time random walk, and we sort of couple the jumps of wt and xt, except where wt's jumps are already prescribed by its past. So that's specifically times t, where wt minus some integer multiple of beta is less than or equal to 1. So when you're within distance 1 of your past at a multiple of beta time. Okay, and so this is what I'll mean by interacting with the past. And for some technical reasons, when we close a path or like a cycle, so return back to 0 at a multiple of beta, integer multiple of beta, I'm going to regenerate the environment. So take all the random these random edges and just resample them. So and this is just going to be a tool. I'll prove results about the original cyclic walk, but this regenerated cyclic walk will be convenient to work with that. But of course, if on the event that the regenerated cyclic walk never returns to the origin, then it's just the same as the cyclic walk. So it's enough to sort of prove transience for that one. But any questions about the model so far? Okay, good. So let me tell you a bit about the history of it. The interchange process comes up in sort of from various directions. One, I think maybe the earliest is in the study of like the exclusion process on graphs and by work of Harris. Diaconis and Shashahani looked at this as sort of for the interchange process on the complete graph, where you can think of it as sort of like a type of card shuffle, where in each, or at sort of rate 1, you pick 2 cards and swap their locations over. And you can study, how long this takes to shuffle. And so Diaconis and Shashahani, and this is one of the earliest works in sort of the theory of mixing times of Markov chains. Maybe it's either the first or the second example where cutoff was approved. And this introduced the idea of using the representation theory of the symmetric group in order to analyze mixing times. So this was an important result. But the result, or the direction that we're looking at, is closer to work by Bowen Toth, who looks like he's watching. So on studying the quantum Heisenberg ferromagnet, and what he showed was essentially that spontaneous magnetization was equivalent to having infinite cycles in this model, except where you add some additional weight of 2 to the number of cycles, if I'm correct there. We're not going to look at this weighted model. We'll just look at the unweighted one. But it'll be okay. And so what can you expect to happen? Well, on Z, and I should have said that this is on ZD. The conjecture is that, okay, there's no infinite cycles when the dimension is less than or equal to 2. We already know that when D equals 1. But then when d is greater than or equal to 3, and the time is big enough, then you do get infinite cycles. So this is a lot like how random walks behave. They're recurrent in dimensions 1 and 2, and transient in dimensions 3 and higher. So it's quite natural to expect that from this point of view. In the past work, there's been sort of various results on this. On the complete graph, Berish, Sticky, and Duret show that there was a phase transition of when you get linear size cycles. Schramm proved Poisson-Dirichlet statistics for it, which is also what's expected in this large beta d greater than or equal to 3 case when you have not ZD, but like a large box in ZD. Bjornberg did the sort of weighted cycles case. And then the results on sort of trees and other sort of high dimensional graphs. So Omer Angel showed that on trees, for some values of beta, you get infinite cycles, and Alan Hammond extended that to all large values of beta, and also showed that on deregular trees for d bigger than 700 and something, but there's a critical value of beta, because you don't really have a monotonicity of beta in this. So it's, it could potentially be that, for one value, for small beta, you don't have infinite cycles, and for some beta you do, then for some slightly bigger beta you don't, and then for some bigger beta again you do. So Alan Hammond ruled that out for high degree trees. There's also work on random regular graphs, the hypergraph, various, and I know I'm missing out various other references, including of people I can see in the audience, so apologies to them, but this was put together sort of a bit last minute, so we'll give a better description of the work when the paper comes out in a couple of weeks. So our result is that when d is greater than or equal to 5 on, should have said again on ZD, then you get infinite cycles for large enough values of beta, and the probability of that is actually, with positive probability, actually with probability quite close to 1 if beta is big. And I mean, actually, if we were like we haven't done this, but if we were more careful, I think we could show that basically the probability of having an infinite cycle is very close to just the probability of a random walk returning to the origin at a time that's a multiple of beta, which is of course like 1 minus beta to the minus d over 2, some sort of 2 pi's and so on. Okay, so how to do this? Well, why it's expected for d greater than or equal to 3. Why do it in only for d greater than or equal to 5? Well, I'm sure many of you in the audience will sort of understand why this should be easier in higher dimensions. But basically, random walks and Brownian motion are less likely to hit their past in higher dimensions. In dimension 3, if you run let's say a random walk up to time t, and then for another time t, and look at how big the intersection of those two paths are, it'll be sort of quite big. Whereas in dimension 5 and higher, you only expect order 1 number of intersections. So if it behaves like a random walk, then in dimension 5 and higher, it should avoid its past, and that will be good for us. So in the spring, Dor and I came and talked to Tom and also Roland Bauerschmidt, who was visiting at the time, and asked about what was known in the higher dimensional case. Are things like the lace expansion applicable? And the answer we got was Basically, probably not, because and I think if I'm summarizing what they said correctly, it was that there wasn't sort of the right sort of self-repulsivity sort of property to sort of have the lace expansion machinery work. So the lace expansion, if you don't know, is a sort of very powerful technique that's sort of been used to analyze walks, things like self-avoiding walk or critical percolation in high dimensions. It was introduced by Bridges and Spencer. Okay, so that was our first thought, but so instead what we're going to do is something more bare hands, and no fancy machinery will be involved in proof of this. So let me give a sort of proposed sort of circular argument for proving this, which is to say, well, okay, if it behaves like random walk, in dimension 5, it should have a minimal interaction with its past. And if it has a minimal interaction with its past, then it should behave like random walk. So if you put those two together, it should behave the way we want. Okay. Now, if you want to make this into something more approximating a real argument, you would want sort of like a series of inductive hypotheses and assume sort of some good behavior up to some time scale, and then prove good behavior up to a bigger time scale, and that's what we'll do. But let me first say, one of the things we want to be able to do is, and to go from one time scale to the next, we want to be able to sort of concatenate walks. So with x1 up to xk were independent, just simple random walks. And these were the sort of driving processes that we used to construct k independent cyclic walks. Suppose and let's say the xi are the black ones and the wi are the blue ones here. So let's suppose that we concatenated together these simple random walks of length t to get a simple random walk of length k times t. So I'll sort of just put them together like this. Okay, so if you concatenate simple random walks, you just get a longer simple random walk. Now I'd like to, so then suppose I concatenate it, and actually let me call this concatenated walk x tilde t. And now let me concatenate together the corresponding cyclic walks, and we'll call that w tilde t. Now w tilde t is not the cyclic walk generated by x tilde t. And the reason for that is, I mean, it will be up to the first concatenation point, but let's say we're at some later point. So we're in some, the interval, let's say w2t here from here to here. When we're working out what, let's say the real walk wt does, well, it has to look back on the full history from time t to time 0. But if we're just looking at this piece of, like this smaller cyclic walk, we just need to it just needs to look back at its history to the last concatenation point. So and those can be different. So the interactions between the two they have two different, their paths look back a different amount of time, so they can have different interactions with it. Okay. So it doesn't have to, so the concatenated cyclic walk and the true cyclic walk aren't in general the same. But if we look at their difference, what we're going to show is that they're going to be, with very high probability, be sort of very close together, like some Tn to the epsilon, or I'm going to put in 3 epsilon here, because that's what we actually have to prove. But so this is sort of one of the main things we'd like to be able to establish, that this happens with very high probability. Any questions about that? Yeah.
Number of things. Before you mentioned coupling between X and W, which are coupled, the jumps are coupled except when
you've already revealed the jumps. Yeah.
What happens in that case?
Well, then you look in the. I mean, in that case, you already know what you're supposed to do based on the past.
For W.
Yes.
And what do you do for X?
So X is just some simple random walk that does its own simple random walk. So X has, jumps to the left, jumps to the right.
I see. So the jumps coincide except when W is forced to make a jump, in which case X does not do it and W does. There
are also times when X makes a jump and W knows that it's not supposed to make a jump at that point because it's at a point where in the past it didn't make a jump. So it can go both ways, but yeah, that's the idea. And we want to understand if we concatenate these sort of driving random walks together, how does that correspond? How does that concatenated walk correspond to or compare to the concatenated cyclic walks? And what I want to show, claim or show is that this difference will be small. So if we're running up to time Tn, it will only be some very small power of Tn. And then if we had a lot of concatenations, and then that's like summing up lots of independent terms, so it should be approximately Brownian. So if we have a result like this, then the concatenated walk should look Brownian, and if W is close to that, then it should also look Brownian as well. So if you can say something about concatenation, then you can show at least some properties about the cyclic walk. Okay, but of course, I haven't said anything about why we would be able to prove this. Any questions?
Can you just say one more time how cyclic walk is defined?
Yeah. So essentially,
just your location after time t in this with the song clocks.
Yeah, and so so it's like after, with the Poisson clocks, we just sort of repeat them mod beta. So we'll have one here, and 2 sort of here. And so, wherever we have a Poisson clock here, we also have ones that, that plus beta and 2 beta and so on. So that's the environment. And then if we want to see where the walk goes, we start at 0 and just sort of follow this path around with this in the cyclic environment.
Right. So all of these things might cycles eventually.
Or they might never return to.
Or they might never return.
Yeah. And so we want to show in high dimensions there's a good chance that they never return.
Right, but if it makes a cycle, then your cyclic walk just goes over, rotates itself a number of times, and then you have concatenate the next thing.
Yeah, and so our regenerated version, if we close a cycle, then we'll resample the environment and start a new one from there.
And that's the point I didn't understand. Once I form a cycle, then what do I do?
Then you say, okay, delete all these green lines and just resample independent ones.
And yeah, okay.
So if we never close a cycle, then this doesn't matter. So if we don't close it, but if we do, then it means that we don't sort of get stuck in the same place all the time for a long time. So that's sort of the purpose of this.
If I started outside Yeah, but when I regenerate the cycle, I'm periodizing it on the way up, right?
Yeah. Yeah, exactly.
I mean, I guess one way to think of it is just put down your bars or whatever, and then you just repeat it periodically all the way up, right?
Yeah, yeah, exactly. Okay, good. Any other questions? Yeah.
How crucial is phosphorus?
Don't know. I haven't. I mean, for today's proof, quite crucial. In general, maybe maybe not. I don't know. What would you like to do instead?
I'm just
Yeah, no.
it's much longer discussion than.
Okay. Yeah. Okay. So let me. Okay. So we're going to do. So it's a multi-scale proof. We're going to do induction on scales. Tn is 4 to the n. And we'll prove a series of properties about the walk up to time Tn. The first one is something about its transition probabilities. If it was random walk, you'd expect the probability of being at u at time t to be at most t to the minus d over 2 divided by some square root of i's. I'll allow ourselves an extra plus 1 over 10 in the exponent here to give us a bit of leeway. But already if we can establish this, then the probability of having an infinite cycle is positive, because sum of
Your W is your cyclic one, right?
W is the cyclical. Yeah, that's right. The probability that W J beta 0 is less than or equal to sum of J beta to the minus d over 2 plus 1 over 10, which is sort of like a constant times beta to the minus d over 2 plus 1 over 10. 10 is 0 beta. Okay, so if we did this inductive assumption, we'd be done. We're also going to assume that it's approximately Brownian. So we can couple the cyclic walk with Brownian motion times some diffusion parameter, which is kind of close to 1, but may depend on the scale. And the discrepancy is going to be
random or fixed?
Is what?
Is sigma n random or a number?
Fixed, it's a constant, yeah. It will be the variance of some random variable.
Thank you.
Deviation. Yeah, and so we expect fluctuations of order square root of Tn. So we ask that the coupling is that these differ by at most Tn to the 2 over 5, except with some really small probability e to the minus n squared. And I'm sort of hiding some details for when Tn is sort of the order of beta or a polynomial of beta, I'll take something a bit smaller here, but I don't want to get into the details of that. And the third property, which is sort of similar to the Brownian motion one, the probability that it goes more than n squared square root Tn is at most e to the minus n squared. And so there's going to be a couple more inductive assumptions, but suppose we knew all of these, and up to, let's say, n minus 1, and then we also knew concatenation. Then I claim that we could sort of, concatenation would be enough to carry out the inductive step. Okay, and that's because we could write, well, Wtn would be very close to W tilde Tn, which I could write as a sum of, where this is a sum of concatenation of, let's say, Tn to the 1/3 Wi's. where these are independent. So this is like a sum of an IID sum. So concentration of IID sums is is easy to do. The KMT embedding, or at least some generalization of that to D dimensions, would say also that we should have a good Brownian approximation to this concatenation. And then if we want transition probabilities, we could do a sort of another concatenation where we say, okay, probability that, let's say WT equals U. I'm going to, let's say tilde. I'm going to do the concatenation now of length T minus Tn minus Tn to the 4/5. This equals V times probability to Tn to the 4/5 minus V. So this is just transition probabilities. This one inductively is less than or equal to Tn to the 4/5 to the minus d/2 plus 1/10. And so overall we get that this is less than or equal. It's less than or equal to that times the probability that W1 tilde T minus Tn to the 4/5 minus U is less than or equal to n squared Tn to the 2/5, because this is, it's very unlikely that this is more than n squared square root of Tn to the 4/5. And then this one you can, behaves the way you expect with according to the Brownian approximation, and then you get overall you get less than or equal to Tn to the 4/5 plus 9/100. So Tn to the minus d/2 plus 9/100, say, and then this is only for this is for a concatenated warp, but the coupling says, okay, we only have to sort of sum over the probability that the concatenated one. Well, I can say probability that WT U is equal to probability that WT tilde minus U is less than or equal to Tn to the epsilon plus the probability that WT minus W tilde Tn less than or equal to Tn to the epsilon. So, and for this, we can take a union bound over U's here, and there's only Tn to the d epsilon of them. And for this one, this is what we're, this is by, our assumption that concatenations work very well with very high probability.
So, Alan, this is going a little
Yeah.
fast. So is this stuff on the right side, the induction steps, to establish the right side, or what?
Yeah. So what I wanted to say is, if we could prove this concatenation bound, and we assumed these induction properties up to n-1, then with concatenation, it's fairly straightforward to get these then at the next level.
But do you need more inductive assumptions or?
Yes.
Yes, you do. And those are the ones, now which ones are you assuming? So I'm,
Okay.
and which ones are you,
Sorry.
and then, yeah.
Yeah. So the induction. So the inductive properties are these three plus two more that have come. And then
Okay, those three on the left, right?
Yeah.
Yeah, and then you have something on the right too.
yeah, so the right was sort of just calculations.
Okay.
Apart from this bit.
Okay.
So
From that definition.
Yeah. Okay.
So the right part is just calculations, which I didn't quite follow.
Yeah. So understandably, given that it was
Trying to understand the structure.
yeah. Okay. So then I want to sort of also add in some inductive assumptions on sort of smaller scale properties.
Okay.
And I'll talk about a time being relaxed. So if we have the walk, say up to time t, it's relaxed at time t if when I draw a ball of radius, let's say this is 2r here, the amount of time that it's spent in this ball is less than or equal to 6 to the power of r. Now, if it was a random walk, you'd expect it to have spent at most 4 to the r time there, so we're being fairly lenient with this. And actually, and I'm only going to count time since the last sort of regeneration. If it hasn't regenerated, that doesn't matter. And so this is for scales where 2 to the r is at least beta to the third. And for radii that are smaller than beta to the third, I want to assume that there's no history in a small ball around t before time t minus beta over 2. So
What do you mean exactly by regeneration time? Just the time that the walk no longer intersects its path?
oh no, so, sorry, the regeneration times were if you close a cycle, then we just sort of start the whole process again.
Okay, thanks.
Okay. So for really small balls here, we can't assume that it spent no time there, but we can say that it only was there recently. It was, if we go back in time more than time beta over 2, then it was never in this region. So at least for a short period of time, it's not going to interact with its past. Okay. And so that's the definition of relax. So why is this a good or useful definition? Well, I wanted to okay. So from time t, I'll define t hit as basically the first time the walk interacts with its past. So the first time s greater than t, such that ws and ws minus k times beta are within 1, when s times k beta is before time t. So the first time that the past before time t became relevant. Does that make sense? And so up until t, so if it so now if I start from time t and I can couple the evolution from time t with a sort of independent cyclic walk until t hit, because because I haven't needed to use any sort of outside information until then. I'm just sort of seeing new or I'm seeing transpositions that I didn't see in the past. Okay, and if we're at a relaxed point in time, the probability that t hit of t is greater than or equal to t plus 4 to the n minus 1, 4 to the n minus 1 being sort of the biggest time I can assume things from our inductive hypothesis, then this is greater than or equal to like 9 over 10 or something like that. So it will be close to 1. So if you're at a relaxed time, you're unlikely to hit your pulse. And the reason for this is, and this essentially follows immediately from the transition probabilities. You just look at the expected number of times you hit your past, and it's small. Okay, so and the walk I'll call relaxed if a 9 of length Tn, if a 9 over 10 fraction of that, or something slightly bigger than 9 over 10 fraction of that is relaxed. So most points along the walk are relaxed. And so our inductive hypothesis is that that's overwhelmingly likely. Most walks are relaxed. And then the last condition is sort of a social distancing condition, which is to say, basically to say, if I take 2 different walks, sort of run them up to time Tn, maybe they intersect each other a little bit, or a few times, but the amount of time that they were close together is small unless they sort of merge together. I mean, you could have one walk sort of comes around and follows the path of another walk in this cyclic process. We'll sort of assume that doesn't happen, or so sort of on the event that that doesn't happen, then the amount of time they're within 1.4 to the n of each other is at most 4 to the n minus epsilon, except with some exponentially small probability. Does that make sense?
Well, is it the fact that they could actually overlap for a long time that can happen? And you're assuming that, right?
I mean, they could.
But that's very rare, isn't it? Or
yeah. So my inductive hypothesis is that's very rare. That they spend too much time.
They do. This is the usual picture.
Yeah, exactly.
And then anything where they follow each other has to be quite rare, no?
It's not. I mean, what we're worried about is that they somehow get tangled up in some weird way with each other, so that we can't sort of, and that they can't disentangle each other from each other. The histories are very dense and complicated. But we're going to assume that this, our inductive hypothesis is that this doesn't happen.
These are walks where each one has its own Poisson generation, or
there's a common.
And a common one,
Yeah.
Isn't it the case that once they merge, they are bound to stick together?
Yeah. So we're saying. No. So if they merge, then they will stick together. So we're saying that. So I want to say that if they didn't merge, then they didn't spend. Then their overlap was small.
What do you mean that they can't get close? It would be more mistake.
Yeah.
So because once they merge here, I think.
Yeah. Okay. Right. They're allowed to merge. That's fine. But if they don't, and they also don't close a cycle, then the time they spent in proximity to each other.
Proximity.
Yeah. It's brilliant. All right. So that's the sum of the inductive hypothesis.
So yeah. Could you highlight them again just to?
Okay. Good. So
what's going on?
Yeah. Okay. So 1 is transition probabilities. 2, Brownian approximation. 3, sort of like large deviations of how far it travels. 4, most paths are sort of relaxed most of the time.
Yeah.
And 5, most pairs of paths that don't merge don't spend much time in proximity to each other.
Did the dimension enter anywhere up to this point?
No, not really. I mean, you know, we have the dimension in the transition probabilities, but I mean, we're certainly assuming d greater than or equal to 5 here, but and I should say, for times before the cyclic time, when these are just random walks, all of these are very easy to prove, just by the properties of random walks.
But where was it that it mattered that d is 5 and not 3? In which of the inductive assumptions, or?
It's to prove that tau heat is large, assuming relaxed.
Yeah, so well, I mean, yeah, so that's true. Yeah, so I mean, yeah, so as Dor said, it's this. If you're at a relaxed point, then you're unlikely to hit your past. That's sort of what we need d greater than or equal to 5 for. That would
Okay, thank you.
Okay, so it's multi-scale. So as you might expect, we're on sort of
Yeah, one last question. All properties are proved inductively, or are the local ones? Do the local ones have a non-inductive proof?
it's all inductive together.
Okay, thanks.
Okay.
And the induction proceeds by concatenation, I suppose, right?
Yeah, so I'm going to tell you some key estimates that we get that make the concatenation likely, and then once you have the concatenation, then you prove like the Brownian approximation, and the others sort of putting those together. The others follow these. Well, okay, not by the way. In a few pages or so. Okay, so we'll have blocks of side length 2 to the L, and I'm going to call a block bad if essentially one of inductive properties 3, the movement one, 4, the relaxed one, or 5, the proximity one, fail sort of for a walk starting in this block when we're looking at times up to 4 to or times 4 to the L over L to the 4. So a bit smaller than what you would need to sort of traverse one of these blocks. And because the inductive properties hold with very high probability, the probability that a block is bad is like e to the minus L squared or something like that. So the probability that any block is bad is very small. And also, if I take blocks that are at, distance a few blocks away from each other, then the event of being bad will be independent, because we only need to keep track of the walks for a short period of time to check if they're bad. So the probability of having more than a constant number of bad blocks will be really small. So just to set some parameters, epsilon is 1 over 200d. I'll let k out the scale that we look for bad blocks on the epsilon squared times n, and q will be a constant that's 1 over epsilon to the 10 times 100d, but just think of it as a big constant. And the probability that you see more than q bad blocks within distance, say 5 to the n of the origin, and it's very unlikely that the walk will travel more than 5 to the n in distance in time 4 to the n, then you'll only see at most q blocks, except with probability e to the minus 100 n squared. So we can sort of throw away that possibility. Okay, so I'll let lambda be essentially the bad blocks with a little bit of a buffer zone around them. And then I'll let lambda plus be the bad blocks with a bigger buffer zone around them. So the first buffer zone will be about 10 blocks wide. The second buffer zone will be q to the 3, maybe, I think actually I wanted q to the 4. Q to the 4 blocks wide. And the point of this is that if we're outside of this outer buffer zone, and I just start a Brownian motion, it might enter the first buffer zone, but it won't enter the inner buffer zones, except with probability, maybe probability a half. Or like with probability a half, it never reaches close to any of the bad blocks. Okay, so the estimates we want are for any block on scale k or bigger, that it's not heavy, that we don't spend too much time in that block, too much time, not too much time, visit too many vertices. Too many vertices will be 5 to the L. For round and walk, you only expect 4 to the L, so this should be likely. But I'm also going to not count the number of vertices in the bad blocks. But because these bad blocks are on a very small scale, if L is greater than or equal to epsilon n, then there's just not enough vertices in the bad blocks to, they'll be much smaller than 5 to the L. So I can count just regular just the number of vertices in B in total that are visited. And so of course, this is the kind of estimate that you would want to show that a point is relaxed. And the other estimate I want, and so then the other estimate that will show is that on any interval of length Tn to the epsilon, at least a 3/4 fraction of those vertices are relaxed, or a 3/4 fraction of the time, I should say, the walk will be relaxed. So these are the estimates that we want. I want to say why 2 means concatenation will work. That if we always can find a relaxed vertex pretty quickly. And the reason for this is, suppose we're concatenating, and now we're at some time t, and we have 2 different, we're comparing wt and w tilde t, and they have 2 different histories. Essentially, the distance in the past that you need to look is different. Okay, so but I claim that for S that's between time t and time t hit of t, minimum time t hit t tilde, the analogous thing for w tilde, that this is that we can couple the walk so that ws minus wt is equal to w tilde s minus w tilde t. So essentially, what they do after this time, but before they interact with their past, is the same. So like t hit and t tilde hit are the times where they start interacting with their past before time t. Okay. And now if we're at a point in time where they're both relaxed, then there's a good chance that both t hit and t hit tilde go on for time 4 to the n minus 1. So the walks will agree for a long period of time, and because of property 2, we only had to go a short period of time, Tn to the epsilon, before we found a time where they were both relaxed. So if we have that, then we can do concatenation and prove the inductive hypothesis. Okay, so in the 5 minutes left, I want to tell you how we can do this. So basically, the idea is we want to say, we're not spending too much time in a block, except maybe one of the bad ones. But we could have a bad block, and the warp kind of enters the bad block, and then it sort of gets stuck. It gets tangled up with itself. It has a really complicated history. And then when it tries to sort of move away from the bad block, yeah, it's not going to be relaxed because there's so much history around it. So that's bad. So we want sort of an escape route to get us away from a bad region. And so the idea is that we can always, if we have now a box on a much smaller scale Z, where so the side length will be, let's say something like n to the 20, then when the warp first enters this box, I claim that there's a good chance, well, no, there's probability n to the minus theta, so polynomially small, but not exponentially small, that the warp from here will sort of move away, and within time, k squared times tk will get distance q to the 4 times tk away. And this is a distance that's long enough to take you away from the outside of the bad region, because there's only q blocks that have side length tk. So why this has a probability that to make this escape is at least n to the minus theta, given the past, and that conditional probability is at least n to the minus theta with very high probability, at least 1 minus e to the minus n to the 4. So why is that? So this is one of our, so this is, well, so imagine this, we have this small scale box, and I'm going to just start a lot of cyclic warps from there, from random locations, and run them for the time k squared tk. And basically, because by our inductive hypotheses, most of these ones won't intersect each other. Maybe a few do, if let's say this one intersects one of the ones we've already seen, we'll just stop it at that point. So we can get a polynomial number of these ones. And okay, and now suppose I just delete the stuff that's in the middle, inside the box. What it's saying is that there's a lot of paths kind of exiting the box. And this happens with very high probability. So now if the warp comes enters this box for the first time, then, well, once it's inside the box, there's sort of no history inside the box to interact with. And there's we can use the inductive properties to say there's a polynomial property that it gets to one of these good exit points and then exits a long way away and sort of makes its escape from the bad region. So this has very high probability. And okay, so, and then we sort of put this all together to say a box on scale L. So this is B side length BL, meaning it's side length 2 to the L. And we want to keep track of how much time the warp spends in here. So we have a series of stopping times, S1, SI, UI, and E to I. And so S1 is going to be the first time that it enters some very small scale block within B. Then from that point, we run it for time. So this is time SI. Then we run it for time up to SI plus k squared 4 to the k, or stop it at the first time we reach a point that's relaxed. And there's a star here, meaning relaxed, except we're ignoring the effect, the amount of time spent in the bad blocks. And and it's outside of the buffer zone of the bad ones. That it reaches a point like this follows from the inductive hypothesis and this escape sort of calculation with probability n to the minus theta. And then once we're at a relaxed point, there's a good chance that it sort of wanders off for time 4 to the n minus 1. And then eta I, so this was ui, this is eta I when we stop it, is either once we've run for time 4 to the n minus 1, or when we hit the past of the walk, or when we spent sort of too long too close to this block. And what you can show is that you get to, you wander off for a long time, for time 4 to the n minus 1 with probability n to the minus theta divided by 2, say. Okay, so not a very high probability, but if I run a lot of trials of this, so then the next S2 will be then the next time I reach a new small subblock B, then I escape for a while to a relaxed point, then I run for another time 4 to the n minus 1 or until I hit the past, and keep iterating these. And the claim is that the number of iterations you do is at most polynomial in n, and that you can, if you add up the total amount of time you spent in B, if you haven't done too many iterations, then deterministically this will be at most, this will be much less. This will be like 4 to the L times n to some power. So much less than 5 to the L. So it won't be heavy. And if the blocks aren't heavy, then these arguments will also say that you got, because the total amount of time you can spend in bad blocks is not that high. So it's just like their volume times beta. So soon you'll enter a good block. That good block won't be heavy. You won't have visited it too many times. So the relaxed path property and the social distancing proximity property mean that you can show that you will soon find a relaxed point, and that actually most points will be relaxed. And so if you, and then that's enough to prove the key estimates. Then these key estimates are enough to prove concatenation, and then concatenation is enough to prove the inductive estimates. So sorry for going over time, but and giving very little details about this last bit, but yeah, happy to talk to people at lunch or thanks for listening.
Questions?
Ron?
What about the quantum Heisenberg for a moment?
Yeah, so we have a good question. I think so. Yeah, so we haven't really had a chance to think about that. I mean, we are using sort of the independence very heavily in here. So yeah, I'm not sure what the chances of saying something about these methods are, but yeah, but we'd certainly like to think about that.
What about once reinforced random walk?
Yeah, so yeah, that might have, I mean, there's various other sort of models where these methods might be applicable. And yeah, we we're sort of busily writing this up because, part because Dor is about to apply for jobs and graduate, and so want to but yeah, so we haven't thought yet about the sort of various extensions, but I think the methods could be applicable in other sort of or models of walks in high dimensions that interact with themselves.
So do you have any guesses about what the walks look like in 3 and 4 dimensions? Are they Brownian motion or some other crazy thing? Diffusive?
So in 4 dimensions, that it's definitely still Brownian motion. Actually, so when we chatted to Tom, his first suggestion was show that you have a good chance of not closing a cycle by like some big power of beta. And sort of simpler versions of these methods work even in dimension 4 for answering that question. Dimension 3, you have more interaction with yourself. I'm not sure. Yeah. And then there's still, of course, the question of dimension 2 as well, and showing recurrence for that one.
On the dimension 2 question, you don't have, this does not give new input.
No, this is very much a high dimensional argument.
There's some questions in dimension 2 which are easier with the Heisenberg than they are. Riemann-Wagner, you have Riemann-Wagner, so you don't have infinite cycles.
But
we don't know how to do
that. Pass the Riemann-Wagner to the discrete.
Should be able to do that. I don't know how to do that. I think we've just been silly, but.
Okay. Well, that's very